Here's a construction timeline that sounds fake. 8 meters tall, 2 full stories, a complete building, done in 22 days, built by a crew of 3 people. That's not a rendering. It's not a research prototype sitting behind glass at a trade show. It's a real standing building, built by a team at China Three Gorges University. And it's already breaking a business model the construction industry has run on for generations. This building was built by a team at China Three Gorges University using a technique that's been quietly maturing in China for over a decade: large-scale 3D concrete printing. 2 robotic arms, guided by a digital blueprint, moved back and forth across the site, laying down layer after layer of a specialized concrete mixture until 15 load-bearing columns and a complete set of exterior walls existed exactly where the blueprint said they should. No lumber framing, no masonry crew laying brick by hand, no months of scheduling delays waiting for 6 different subcontractors to show up in the right order. By the end of this video, you'll understand exactly how a process like this compresses months of work into weeks, why the American construction industry is watching this far more closely than most people realize, and where this technology genuinely still can't compete. To understand why this matters, you have to understand how badly the traditional construction industry needs a fix. In the United States, building a typical single-family home takes somewhere between 6 and 12 months from groundbreaking to move-in, according to National Association of Home Builders data. That timeline isn't really about the physical difficulty of stacking materials on top of each other. It's about labor, framing crews, electricians, plumbers, drywall installers, painters. Each trade shows up in sequence, and if any one of them is delayed, backed up, or short-staffed, the entire project slips. And American construction has a serious, well-documented labor shortage. Industry estimates put the shortfall at several 100,000 skilled workers nationwide, a gap that's only gotten harder to close as the existing workforce ages out faster than new workers are entering the trade. That shortage doesn't just slow projects down, it drives up labor costs, which get passed directly into the final price of every home built. That labor cost isn't a small line item either. On a typical American home build, labor alone routinely accounts for somewhere around a third to nearly half of total construction cost, depending on the region and the trade mix involved. When a shortage of workers pushes wages and scheduling delays higher at the same time, that's a direct compounding hit to the final price tag a homebuyer pays, which is exactly the layer of cost a printer with a 3-person crew is designed to compress. China's 3D printing approach attacks that exact bottleneck. This isn't actually a new idea for Chinese construction firms. A company called Winsun made global headlines back in 2014 by printing 10 complete houses in 24 hours at a cost of roughly $4,800 each. Winsun later scaled the same core technology up to a 6-story apartment building and an 1,100 square meter villa, using a purpose-built printer roughly the length of half a football field. That's the part worth sitting with for a second. This isn't a single lab demo that got lucky once. It's a technology that's been through more than a decade of iteration, moving from 10 identical small houses printed as a proof of concept to a functioning multi-story apartment building, to now a fully engineered, code-compliant structure built by a university research team using an even more refined process. This university project isn't a first attempt at this. It's the decade of refinement that followed those early headlines finally producing a small, clean, replicable structure. Here's how the physical process actually works. The printer's robotic arms extrude a specialized cement-based mixture, often blended with recycled construction waste like crushed glass, steel fiber, and reclaimed aggregate. That mixture is engineered to be fluid enough to pump through the printer nozzle, but stiff enough to hold its shape immediately after being laid down, so each new layer can be printed directly on top of the last one without waiting for it to fully cure. Layer by layer, walls and columns build upward with a level of geometric precision that's difficult for human bricklayers to consistently match by hand. The precision matters more than it sounds. A human mason working with brick or block naturally introduces small variations, a slightly uneven joint here, a millimeter of drift there, that get absorbed into the finished wall without anyone thinking twice about it. A robotic printer follows the exact same digital path every single time, which means load-bearing walls come out dimensionally consistent from the first layer to the last. That consistency isn't just a nice to have. It directly affects how a structure distributes weight and stress, which is part of why these printed structures have held up to standard engineering safety reviews in China, despite looking on the surface like nothing traditional inspectors have dealt with before. Some of the more advanced Chinese printed concrete projects have gone a step further, embedding real-time structural sensors directly into the printed material itself as it's laid down. Those sensors continuously monitor things like vibration, stress, and strain throughout the life of the building, feeding data back to engineers long after construction wraps. Retrofitting that kind of monitoring into a traditionally built structure typically means drilling into finished walls after the fact. Here, it's baked into the building from its very first layer. There's a cost story hiding inside this technique that matters just as much as the speed. A separate Chinese 3D printed bridge project using similar layer-by-layer robotic printing documented cost savings of roughly 2/3 compared to a traditionally built structure of the same size, largely because the process eliminates wooden formwork, reduces material waste, and needs a fraction of the on-site labor hours that traditional construction requires. And that math is exactly why some American construction firms are quietly paying very close attention to a manufacturing process most of their customers have never heard of. If you want to see exactly why and where the real limitations of this technology actually are, stick around and hit subscribe, because it's not as simple as printing your way out of every construction problem. To be fair to American innovation here, the United States isn't standing completely still on this front. Companies like Icon, based in Austin, Texas, have been 3D printing homes domestically for several years now, including affordable housing developments and even structures for the US military. But the pace and manufacturing scale China has demonstrated, going from individual houses in 2014 to full apartment blocks and now standardized, rapidly replicable small buildings a decade later, still outpaces what's currently happening at scale in the American market. Now here's the honest limitation, and it's an important one. This particular building is genuinely small, about 1,100 square feet, roughly the footprint of a modest American starter home, not a skyscraper or a large commercial structure. 3D concrete printing today is still fundamentally a walls and structure technology. The printer doesn't install plumbing, electrical wiring, windows, doors, insulation, or a roof. All of that still requires traditional skilled trades to come in after the shell is printed, which means the labor shortage problem doesn't disappear entirely. It just shrinks to a smaller, more specialized slice of the overall project. Think of it less as replacing a construction crew and more as replacing the single slowest phase most crews go through. Framing and structural walls, historically weeks of scheduled labor, now compressed into a printer running largely on its own for most of a month. Everything that happens after the shell is finished still looks close to a normal construction timeline, just starting from a much further along point than usual. There's also a material sustainability angle worth mentioning, because it's a genuine advantage rather than just a marketing talking point. A meaningful share of the print material in these projects comes from recycled construction waste, crushed glass, reclaimed aggregate, industrial byproducts that would otherwise end up in a landfill. Traditional construction generates enormous volumes of waste from cut lumber, packaging, and demolition debris, a process that both uses less raw material and repurposes waste from other projects is solving two problems most homebuyers never think about, but that materially affect the total cost and environmental footprint of a build. There's also a regulatory reality that matters a lot if you're thinking about this from an American perspective. Building codes in most US states were written with traditional framing and masonry construction in mind. Getting large-scale 3D printed structures through permitting and inspection in most American jurisdictions is still a slower, more uncertain process than the printing technology itself, which is part of why adoption here has lagged behind the raw capability on display in projects like this one. There's also a use case this speed unlocks that goes well beyond ordinary home construction: disaster relief and emergency housing. When a hurricane, earthquake, or wildfire destroys hundreds of homes at once, the traditional construction timeline of 6 to 12 months per house means displaced families can spend a year or longer waiting for permanent housing. A process that can stand up a structural shell in 3 weeks with a 3-person crew changes that math entirely. It's the difference between temporary shelters stretching into a second winter and families back in permanent homes before the next storm season even starts. So what actually broke here? Not the need for skilled trades entirely. Plumbers, electricians, and finished carpenters aren't going anywhere anytime soon. What broke is the assumption that the structural shell of a building, historically one of the slowest and most labor-intensive parts of any construction project, has to take months and dozens of workers to complete. A 3-person crew building a full 2-story structural shell in 22 days rewrites what fast is even supposed to mean in construction. And once that becomes normal in one country, it puts real pressure on every other country's construction industry to explain why it still can't.